Hello. Yesterday we left off on Thomson's, and now we're going to go ahead and continue on with the history of the atomic model. So Rutherford. So this what occurred in 1911. He had the gold foil experiment. Just out of the way. He expected that alpha particles will be deflected a small amount if Thomson's model was correct. So what Rutherford did, he shot a beam of alpha particles, which are just helium nuclei. He shot it at a thin sheet of gold foil. And if Thomson's model was correct, okay, we had the plum pudding model, just a solid sphere. If Thomson's model was correct, the beam would go straight through. Kind of like this. If Thomson's model was correct, you would just see a whole lot of that happening. The beam would go straight through, nothing special. He thought they would go straight through because positive charges were thought to be spread out evenly, and alone they were not enough to stop an alpha particle. I like to use the analogy of a semi-truck plowing through a parking lot full of bicycles. The semi-truck is not going to be stopped by the bicycle. It's just going to go straight on ahead. So he was expecting this. Simple, nothing to it. Again, because he thought the mass was evenly distributed and the alpha particles would just go straight through. But instead, he got something that looked like this. Some went straight through. You can see that some did go straight through, but this beam that came out of the other side is a lot thinner than the initial beam that was shot out. So what happened to the rest of them? They deflected everywhere, all over the place. Some even shot straight back at him. Rutherford was amazed at these results. He was known to say that it's like shooting a giant shell at a piece of tissue paper and the shell coming right back at your face. That's how he described it. He was amazed. So what actually happened, okay, you can see, let me put the tracers in there, okay, it's deflecting. Some go straight through, but some get deflected. And look what they're being deflected by, the nucleus. If you show this from the nucleus, like zoomed in on one individual nucleus, you can see if it gets close to it, they get deflected. So that's what was happening. Deflected everywhere. Here's how we explained it. The atom is mostly empty space. That is why some alpha particles were able to go straight through. There is a small, dense, positive piece at the center. That is what was causing the deflection from the alpha particles. They get deflected if they get close enough, because positively charged center, positively charged alpha particles, what alike charges do, they repel each other. Well, here's what happened. Like charges repel, opposite charges attract. So he added the nucleus to Thomson's model. So Dalton's model, if you remember, it was just that single solid sphere. Thomson added the electrons, just randomly thrown in there. Rutherford added the nucleus. He stated that electrons moved around and that the atom was mostly empty space. So now we're up to 1913 with Bohr's model. Whenever people think of electrons, the image that pops in their head is going to be Bohr's model. Now, they may not know that's what it is called, but it is Bohr's model. He claims that electrons travel around the nucleus in orbits of certain energies, like planets around the sun. The planetary model, right? You have the nucleus, You have the electrons traveling around it. In order to get from the ground state to an excited state, that is, in order for an electron to move from an orbit close to the nucleus to an orbit far away from the nucleus, the electron must absorb a certain amount of energy he called a quantum, okay, and to go back, to get from far away from the nucleus to an orbit closer to the nucleus, however much energy that electron initially absorbed, now it's going to emit energy to move back towards the nucleus. Okay, further away from the nucleus requires more energy. Kind of like climbing to the top of a ladder requires more energy. There's no in-between energy levels. You're either on one level or another. And here's Bohr's model. Okay, one electron, if it wants to move away from the nucleus, it has to absorb energy. And then if it wants to move back towards the nucleus, it's going to emit energy. Now, whenever electrons emit energy, it emits it as light and some as heat. So that's what we see. Then enters Schrodinger's quantum mechanical model. Schrodinger was next with his quantum mechanical model. The problem with Bohr's model, one electron right here, right? Remember, what's the charge of an electron? Negative. What happens if I have an electron here that absorbs energy to jump up to another energy level, but I have a second electron here, right? Those two are going to repel each other. So how does that work? Bohr's model couldn't explain that. So we have Schrodinger's quantum mechanical model. Bohr's model cannot explain the behavior of atoms that have more than one electron. His model cannot account for the repulsion force between moving electrons. So the quantum mechanical model tells us that energy is quantized and comes in chunks. That's basically agreeing with Bohr. A quanta is the amount of energy needed to move from one energy level to another. So these first three bullet points, pretty much agreeing with Bohr. But this fourth one is what's brand new to the quantum mechanical model. Electrons have properties of both waves and particles. So electrons behave like a wave. You know, a wave spreads out. Think of throwing a pebble in water and you see the waves go out. That's how electrons behave. But they're particles, but that's how they move. They have this dual nature. Heisenberg uncertainty principle, we can never know the exact location and velocity of an electron at the same time. Since we need light to see, when light is used, the particle absorbs it and jumps to another location. So what this means, electrons are so incredibly small that when a photon of light hits it, it's like it's absorbing that energy from the photon and it jumps someplace else. Imagine you're in a dark room with a flashlight and you're searching for your keys. Anytime the flashlight spots the keys move to another dark corner. So you kind of have an idea of where it is, but you'll never know for certain because every time you observe it, it moves. That's what's happening here. It took 3 years to develop the quantum mechanical model. Energy levels for electrons, the orbits are not circular. Okay, the quantum mechanical model tells us the orbits have these funky looking shapes. We'll get into that in a later unit. They are a region in space. They're not clearly defined routes, paths that the electrons take. It's just more of an area, a region of space, an electron cloud. Think of a airplane propeller. When it's moving so fast, all you see is a blur, right? A circular blur when you look at an airplane propeller. You know that a propeller blade is somewhere in that blur, but you don't know exactly where because it's just moving too fast. That's kind of how it is with the electrons. They move so fast. So when we observe them, we just see this blur and we call it a cloud. So we know an electron is somewhere in that cloud. The more dense the cloud, the higher the probability is of finding an electron there. An area where the chance of finding an electron is the electron cloud. It's broken down to 4 quantum numbers. Okay, we'll get into that later. But here is the quantum mechanical model. Okay, this is what it looks like. The more dense the cloud, the higher the probability of finding an electron there. That's why around the nucleus, it's a bit darker than on the outside. Okay, now we don't know what evidence we're going to have 100, 200, 300 years from now. We don't know if the model of the atom will remain like this or if it'll change. We'll add something to it, we don't know. But with the evidence we have today, this is the closest representation of the atom, of what the atom looks like. Now you do have to know every single atomic model in chronological order. But here's an easy way that you can remember that. Does Donald Trump refuse bad questions? Democritus, Dalton, Thomson, Rutherford, Bohr, quantum mechanical model. Does Donald Trump refuse bad questions? Okay. Alrighty. Thank you for watching, and I'll see you next time. Bye.